So what did we study last class? We started off with fully differential op-amps. So let's have a quick overview of what we did. So we started off with the motivation for fully differential op-amps. So you have some common mode signals which you want to reject. So for example, the example we took was ground. It could be VDD, it could be anything else, right? We also saw cases where you could have signals coupling in from some wire running nearby, okay, onto your signals. And we made the distinction between fully differential circuits and pseudo differential circuits. Yes. Yes, but the difference is the common mode gain is equal to the differential mode gain. You're right. If everything else being perfectly matched, right, you would get the common mode signal would get cancelled. But the difference is the common mode rejection ratio, which is defined as the common mode gain to the differential mode gain, right, is 1 in this case. In the other case, it's very small. Okay. Sorry. Okay. The comparison could probably come when, if you have mismatches. In the presence of mismatches, what would the common mode gain be? What would the differential mode gain be? This one would always be much better than the other case, right? Okay. The other thing we noticed is that the output common mode is also sensitive to the input common mode, right? The output, in this case, for example, we looked at the output bias. If you change V bias, the current changes, therefore the output bias changes. In the other case, it doesn't. Okay. So finally, we want to achieve something like this, very similar to the single stage op amp. There's not a lot of difference. And fundamentally, we decided that we want to go for, we started off with the active load because it looks to be better than the resistive load. And we decided to remove the diode connection here and bias it slightly differently. Okay. So one thing we found was that if you have mismatches between the currents through the PMOSes and the current through the bottom, you could have a problem, right? Where you would, because of the high impedance at that node, to match the currents, it would try to drive it into triode region, one or the other. So we decided we need something like this. Okay, so we need a common mode detector which detects, in this case, if you assume that VOP and VON are the outputs, you want something which generates VOP plus VON by 2, which is the common mode, right? Then something which detects that, you amplify that and then feed it back. Now, we didn't discuss this yesterday, but you really could feedback here. You could have current sources here, you could bias this separately and send this and feedback to the bottom current source, right? There's not a lot of distinction between the two things. At the end of the day, you have two current sources which are trying to match. You could generate a bias voltage which connects to the bottom current source also. Okay. And we found that the simplest case was using a resistive divider, right? Or rather not a resistive divider, it's just two resistors and you take the central point which gives you the common mode voltage. Okay. And we also found that the simplest way of adding this amplifier was to have no amplifier at all, right? This is the kind of the I don't know, the trivial case, right? So you connect it just like you would with the diode connected case, except you connect it through resistors on both sides. Okay. So the output is biased at VDD minus VSG 3/4. Okay. So the output bias is decent, somewhat well defined. Maybe not at the point where you want, but it's well defined. Okay. And what is the gain of this? The differential mode gain. So let's say, okay, let me draw it separately in a slightly bigger form. I'll call this some VB and 1, 2, I'll call, okay. So what is the small signal current through these guys? Actually, what is the total current? Let me call this I1 and I2. What is I1? The total current. I0 by 2 plus GM1 VI by 2 is I0 by 2 minus, okay, these are the two currents. What are I3 and I4? Correct? Yeah. I3 will be equal to I4, which is I0 by 2. That's what your common mode feedback circuit has done. Right? You have basically tried to create perfect current sources. Okay? So then what happens to this signal current? Flows through RCM, right? So you'll have I0 GM1 VI by 2 flowing through RCM. Okay? So you have GM1 VI, oh yeah, GMVI, correct. Okay? Okay. Well, actually in this case it is GM1 VI by 2. This is, you have I0 by 2 flowing like this, right? So you just have a circulating current of I0, which is GM1 VI by 2. Okay? Okay? So that current just circulates like this. So what is the gain of this? Well, right now when we said all of I0 flows through RCM, we have said that we have assumed that M3 and M4 don't have any output impedance, M1, M2 don't have any output impedance. So in reality there will be signal current flowing through all of these. What is it? Correct? Sorry, you said something? No. Somebody said something? Sorry, with this thing in my ear I can't hear very well. So you'll have to speak up a little bit. Okay. So the actual gain is actually RDS3 parallel. This is the differential gain, right? Differential input, differential output. It's GM1 times RDS3 parallel RDS4 parallel RCM. Okay. So in other words, definitely your RCM is going to try to bring down your DC gain. Okay. But we'll go ahead with this first, but this is a point to be noted, because you ideally want your common mode detector to have infinite input impedance. Okay, so it won't affect DC gain at all. Why is that? Right now we have started off with a single stage differential op-amp. Okay, this is actually a single stage differential op-amp. Okay, so you cannot afford to give up on DC gain, just like the case with a single ended op-amp. Okay. So let's go back to this. So let us say you want to set the output DC voltage a little bit differently to what you want, right? So we saw that ideally you want to set it to VDD by 2, correct? So M1, so this is I0. Okay, and of course remember that for free you actually get some parasitic capacitance here too. Just remember that, because we discussed that if you want to make large resistors you will get some parasitic capacitance, plus you will also have the gate capacitance and other things at that node. Sorry, big mistake. Okay, you will also have the gate capacitance at that node. Okay, now let us say you want to go back to the old structure where you have actually generated this voltage. You want to send it through an amplifier and generate this. What would you use for this amplifier? This is what we started off with yesterday, right? This is what we started off with. We use the resistive common mode detector. Okay, now we need to decide. So common mode detector, we put in a resistor, pair of resistors. What do you do for this op amp? For this amplifier? You know several kinds of amplifiers, right? We have studied a lot of amplifiers. A common source. Okay, but I thought in yesterday's class we discussed that common source is not great. Common drain. If you don't want amplification, you can use common drain. Correct. Common drain, we'll come back to it, but the source follower, we know that there is a DC shift, right? So it may not be the ideal, but we'll see. It can be worked into your amplifier. Okay. What else apart from that? What is that? We can add a single stage common. The single stage op amp you can use here, right? Ideally you have a differential input, single-handed output. You can use a single stage op amp here, correct? So let us, I don't know if I heard you. Is that what you said, single stage op amp, or you said single stage something else? Single stage op amp. Okay. So M5, M6, M7 and M8. Now this guy can be your usual differential to single-ended with the active load. Okay, so these are your inputs, Vi by 2 minus Vi by 2. Okay, how do you connect this? Which input goes where? Gate of M5, where does it go? Okay, first of all, this is the output, right? So I think there's no question about where that goes. Where does which input goes where? Come again? This is yours. So you have one and you have the other, which is VCM ref. Goes to M6 gate. Okay, very good. And this one goes here. Okay. Is that clear to everyone? You need to do it based on the signs. Right? This needs to go to the positive, this needs to go to the negative. So this thing goes to VCM ref, this thing goes to, is that clear to everyone? The gain from here to here is negative, right? Everybody knows that. That should be, clear, I hope. Okay? So now you have connected this up. So the purpose of this common mode feedback loop is to make this VOCM equal to VCM ref. Right? What will it actually be? If you just put any old op-amp, will it be exactly equal to VCM ref? What will it be equal to? You will have some difference based on the common mode. Only if the loop gain is infinite, that voltage will be exactly equal to VCM ref. Otherwise, you will always have a small difference. Right? Correct? Okay? But is there some other way to make sure that even if the loop gain is finite, can you make this voltage equal to VCM ref? Use a different VCM ref. No, not much more higher. Okay, so see, the idea is you don't want to, that is a very inelegant way of doing it. You want to find out a very nice way. I mean, if the loop gain, let's say the error is 0.1 volts, or you don't want to increase VCM ref by 0.1 volts. Now the next question is, how do you generate that 0.1 volt? How do you know that's accurate? Right? You don't want to get into that at all. So how do you make sure that this voltage is equal to VCM ref with no systematic mismatches? Random mismatch is a totally different thing, right? Okay, so if you want these two to be equal, what you actually need, what is the voltage here? So let us say I disconnect this first. Okay, I open the loop. When will it have no systematic mismatch? Systematic offset, I mean, not mismatch. When? VGS for M7. So the voltage here is at if there are no mismatches, the voltage there is VDD minus VSG7. Correct? What is the voltage here? That is what you want it to be finally. VDD minus VSG4. Now of course I should be careful. This is at I0 by 2. If I call this current I9, this is at a current of I9 by 2, right? Now we have not fixed the currents yet. Okay? So this you want to set it to VDD minus VSG4 at I0 by 2. The other one is at VDD minus VSG7 at I9 by 2. How do you make sure there is no systematic offset? Exactly. If these two are equal, if these two values are equal, then when you complete the loop, right, there will be no systematic offset between VOCM and VCM ref. Does everybody see that? Correct? Right now I am assuming, of course, random mismatches you can't do much. You have other techniques to take care of it, right? It's a random effect. Ideally, I mean, yeah, you can use larger transistors and so on, larger areas, but there's not much you can do about those random effects. That's a fact you have to live with. You can at least get rid of the systematic offset. That's what we have been studying so far, right? Number one, first thing you do is eliminate systematic offset, systematic mismatches. Next thing, find out techniques to minimize random mismatches. That is the best you can do with any circuit, right? Okay. Okay. So how would you do this? I think you mentioned something. Make them same sizes. Do you want to make them the same sizes? The current density should be the same. That is all you need. Okay. Because remember, this is the main op-amp you are trying to design, right? You may be designing for a certain slew rate, certain gain, certain, so the current is decided by that, right? In the main op-amp. That could be, 100 microamps, maybe a few milliamps even. You don't necessarily want to burn the same amount of current. That you are effectively doubling the current in the common mode feedback loop. You don't need to do that. Okay? You can always choose that, you can just scale down the second op-amp, right? Such that it uses maybe 1/10 the current, 1/10 the size. Current density is the same, still don't have any offsets. Right? You could do that. Right? This is your current density. Is that clear? Actually, I not by 2 if you want to be absolutely correct, but yeah. Oh. So you can just scale down the sizes. Yes. So right now I'm assuming all the lengths are the same, right? Only if you have the, so you actually want to make the lengths the same, so that those, because that will add another dimension of mismatch, right? If you make the two lengths the same, remember that there are lots of parameters, device level parameters, which depend on length, right? You would have known from your simulation that VT, for example, depends on length, right? So there are other parameters which depend on length. You don't want to disturb those, so you ideally want to use the same length. Only the width you want to scale. Yeah. Yes. Okay. So let us say this has some gain. This op-amp has some gain, right? So let us say VDD minus VSG4 was slightly different from VDD minus VSG7. Now let's say you go ahead and connect this. You are basically forcing those two to be equal. The loop will then create a difference in this voltage. This one is fixed at VCM ref, right? So the loop will change VOCM. So what can happen? The only thing that can change now is VOCM. So the loop will adjust VOCM with a small offset from VCM ref such that these two are equal. Is that right? So now that offset from VCM ref will be given by the gain of the loop, of the common mode feedback loop. Correct? If you already ensure that there is no systematic mismatch between these two before connecting, once you connect there won't be any change. So everything is completely symmetric, so this side will be equal to that side. Is that right? Okay. Okay, so in general you will get something like this. You will have an offset which will be divided by the gain of the common mode feedback loop. Okay. So that is as far as your gain goes. What else do we need to ensure? You have taken care of systematic mismatch, you have tried to make sure. What else? What else do you think of when you have a feedback loop? Stability. Right? Now the minute you have created this feedback loop, you have to worry about stability. You have to worry about, right, how many poles you have, right, gain margin, phase margin and everything which goes together with that. Okay. Now what we'll do is, to analyze the stability, we need to draw the, now we are interested in the stability of the common mode feedback loop. So first we need to draw the common mode equivalent circuit of the overall system, right, and then find out the loop gains, find out the poles, zeros, analyze it. Okay. So if the common mode, this circuit is the differential part, right, so you can just fold it over and have a single circuit. This section of course is not, because it is part of the common mode feedback loop. This is I0, this is M12, actually this is what you are generating. Okay. Is this right? Okay. So what do you need to do first? So does this mean, what is, which is 14? So what do you do if you want to, if you have a differential circuit and you want a common mode picture, what do you do? We just fold over the differential part. Don't remember. That means you should go read it. You should go study it. Okay? But that's what we do. Okay? So you fold over the differential part, right, and analyze the common mode picture. How did we analyze yesterday? I thought we did something very similar yesterday. Well, we discussed the when we discussed the common mode gain of this, for example, I said exactly the same thing. Right, you fold over one side and then find out the gain. That's the common mode gain. Okay. So this M12 is just M1 plus M2 and M34 is just M3 plus M4. Okay. So now how do you analyze this? This is your common mode feedback loop, like common mode equivalent circuit with the feedback loop. How do you analyze this? Look at this portion. Look at these two portions. What are these? First of all, what is this? What is it? It's a cascode current source. You only have V bias. It's a cascode current source. What is this portion? Actually, it looks very similar to something you have seen before. What is it? It's a two-stage op-amp, right? You have a differential pair with an active load followed by a common source, CMOS. So most probably this is going to require compensation, right? So you have something like this. You have something like this where this is a two-stage op-amp with unity gain feedback in this case, unity gain DC feedback. Correct? So you most probably require compensation. Okay? So how would you put the compensation cap? Between the gate of M3 and you put a compensation cap here, exactly the way you did for the two-stage op-amp. So definitely the compensation is one big thing which is missing here. You have to add it. Okay. What would this look like? Okay. First of all, before that, you can also potentially add it here. Okay, because you actually have a capacitive path through this. Okay, potentially, but yeah. If you add it here, this seems like the most natural thing, so let's start off with that. Let us say you add it there. What does it look like in the differential picture? Okay. Okay. So this is your two-stage op-amp. Okay. If you draw an equivalent circuit like a block level diagram of this, you have a two-stage op-amp, which is the portion which is done in blue. Maybe I should have done this in red. The one done in blue is a two-stage op-amp. Correct? It has a differential pair with an active load followed by a common source with an, correct? So this looks like this. So it looks like a two-stage op-amp with unity gain feedback. Correct? So now you definitely know it needs to be compensated. In the two-stage op-amp, the most natural place to put the compensation cap was drain to gate of the second stage PMOS. Okay. Now let's say you put in a capacitance CC. So now you know we won't discuss that anymore. You know how to do that. Okay. What does it look like in the differential picture? What is it? What does it look like here? Yeah. Which capacitor is very large? CC. No, CC idea is to not make CC very large, right? It's a compensation curve. You're using the Miller multiplication effect, right? So CC is probably not going to be very large. Okay. What I'm asking is, the capacitor is between these 2 points in the common mode picture. What does it look like in the differential picture? This is a composite transistor, M3 and M4 folded on top of each other. What does it look like in the differential picture? You'll have two capacitors. What is the value? CC by 2. Only then if you fold over, you have two capacitors in parallel, it adds up. Correct? So in the common mode picture, you have, in the differential mode picture, you have two capacitors of value CC by 2 between drain to gate of M3 and M4 respectively. Is that clear to everyone? Okay. Now, the value of CC, what happens if it's very large? Do you want to add extra margin? Let's say you had the option of making, unity gain frequency much lower. Would you do it? Well, you'll note that now if you go back to the differential picture, CC actually loads the differential outputs. Okay, you definitely don't want to make CC very large, right? So you don't want to overcompensate the loop, the common mode feedback loop. Okay. Now one last thing which I forgot to mention when we did this. We talked about these two having the same current densities. Okay. We talked about these two sets of transistors having the same current densities. Okay. This is a kind of biasing called replica biasing. And it's extremely common in many different kinds of systems. What you're trying to do is, you're trying to get rid of systematic offsets or systematic mismatches by creating replicas of some particular transistors. Okay? Replicas in terms of current density. That itself is good enough. So, several different kinds of circuits use this. We'll actually look at one more type of circuit which uses this. But let's go back to this, the block level diagram. So we discussed what this amplifier is going to look like. We discussed resistive kind of detector. Can you use some other kind of detector? Now the resistive detector has a problem because it changes the DC gain of your circuit, of a single stage differential op-amp. Okay? So you want to avoid that if possible. So you want to make input impedance infinite. So let's go back. What do you want to generate here? You want to generate VON plus VOP by 2. Okay? How else can you generate it? Can somebody think of some ways? Huh? Capacitor. You are trying to stabilize the common mode, right? Including DC. Putting two identical capacitors will not, okay, yeah, but you definitely don't want to do that because it's going to first of all load the differential gain. Okay, so don't even think of capacitors, something else. So this is, what is this? VOP. This is VOP plus VOM by 2. What did you say? Did you say something? A private joke? Or no, I was just curious. Did you say something relevant to the circuit? Or not? Okay, that's fine. What is it? Of course. So, by the way, irrespective of how you sense this, you have to do that CC, right? That you have to put in. You don't have a choice. Now, the question is whether you would choose to put in extra capacitance. I thought we just talked about not putting in, over designing for CC. So we shouldn't talk about putting extra capacitors. Okay? Okay. So what is this voltage? VOP plus VOM by 2. What is this current here? Signal current, of course. The DC current is I9 by 2. The signal current is VOP VOP plus VON by 2. GM5 times that is the signal current. Okay? So how do you, so ideally you want to generate GM5 times VOP plus VOM by 2 signal current on the left hand side branch. Can you think of some way to do that? Some very simple way. Okay, yes. what happens? Connect two branches. So, okay, so you can think of two branches, one branch having GM5 VOP by 2, other branch having GM5 VON by 2. How do you generate that? Well, the simplest way I can think of is split M5 into two transistors, connect the gate of one to VOP, connect the other gate to VOM. That will accomplish exactly what you are trying to do. Is that right? You don't seem very convinced. Okay, let's try that. Okay, I'm going to copy some of this. Yeah. No longer need this stuff. Okay. Rest of the stuff remains the same, of course. So you still need this CC, right? This is your M34 and so on. So everything else remains the same. Now if you do this, you get GM5 VOP by 2 on one side, GM5 VON by 2 on the other side, and then you add the two. Okay? What is the problem with this? When you compare it to the resistive detector. Definitely input impedance is infinite. Okay, so your DC gain is not changed. What's the problem? Noise. Why is noise a problem? You have just taken M5 which was already there and split into two. So noise is not a problem. Okay, so that is, but systematic, yeah, you'll have some random offset. Okay. Anything else? So if you look at the resistive detector, let us say so this we are discussing everything with respect to a single stage op amp. Okay. What is the output swing? We have not discussed that at all. Output swing can be quite large. Okay. The resistive detector gives you VOP plus VOM by 2 irrespective of how large the swing is. In this particular case, this detector is linear only for very small swings. So the current is GM5 times VOP plus VON by 2 only when VOP and VON are very small. Correct? If the swings are very large, then the transconductor is no longer linear. Okay? Think of the case, for example, when one side is very large, the other side is P is very large, VON is very small. That is a common mode. Okay? What will happen is, one side will carry all the current, other M5 by 2 may carry no current, for example. Okay? Okay. So maybe we'll come back to this common source. Somebody was saying talking about a common source. But by the way, we talked, okay, before we get there, so we know that Rn is infinity, we know it's non-linear. Okay. So if you had to use this, where would you use this? If you had to use this, so maybe in a single stage op amp this is not very useful. Okay, because you could have very large swings. Okay. Where would you use this kind of detector? Yeah. You could use this in a two-stage op amp. In a two-stage fully differential op amp, this can be used to set the common mode feedback of the first stage. Correct? Because the output of the first stage is not going to swing much. Remember, we don't have in the two-stage op-amp, a lot of the gain comes from the second stage. Right? And first stage is where you concentrate on getting the DC gain, because the second stage might be driving a resistive load. So you try to get most of the DC gain from the first stage. So you definitely want Rn, equals infinite in the first stage. It is okay if it's, because signals the levels are small, it's enough if it is linear for small signals. So you could use something like this in the first stage of a two-stage op-amp. So we want to take care of loading, and somebody was saying something about using a common source, or rather a source follower. Okay? What is this voltage? So let me call this MB1 and MB2. Is that it? Minus? I just call it VGS-B1. Correct? This is what it's going to be. Correct? Suppose you take this. Will this work? So this one gives you Rn equals infinite, so which is good. You didn't want to load, so this one gives you Rn equals infinite, but it gives you a DC shift. Well, this common mode feedback loop will set your output common mode to VCM ref. What will it set it to? It will set it to VCM ref plus VGS. Correct? Right? The loop is going to try to set VOP plus VON by 2 minus VGS B1 equal to VCM ref. So VOP plus VOM by 2 will become equal to, that is your output common mode, that will become equal to VCM ref plus VGS. And you know VGS depends on VT, it depends on mu, Cox, so it's definitely going to vary all over the place with over process, temperature, right? You don't want that. So what do? Bring in a component of VGS, sorry. Correct. Can't you? Exactly. So you actually want this, right? If you do this, then your VOP plus VOM by 2 will become VCM ref. How do you do this? Exactly. I mean, you just do exactly the same thing which you did for the other cases. Right? We call this MB3. Minus VGS3, VGSB3. So what do you need now? What is the condition then for no systematic offset? same current densities, not just the same current, right? Again, this is another case of replica bias. Okay? Okay? So you need to have the same current density in MB3 and MB1, MB2. Okay? What else? What else does the source follower do? It gives a DC shift, okay. What else? It gives a gain which is could be slightly less than 1. Okay? Because it's something like GM, or it gives you somewhere around 0.9 maybe. Is that a problem here? Not a major problem, because as long as one that is a replica of these, you would have similar gains. Forget about random mismatches for a moment. I'm talking about systematic mismatches. Right? If you have some gain alpha less than 1, you would have gain alpha less than 1 for all three. That won't be a problem. What will it affect? It will affect your overall loop gain of your common mode feedback. Correct? If you have a gain of 0.9, instead of having a loop gain of I don't know 100, you may have 90. Okay? So that means that you'll have to take care of this gain in the overall loop gain.